Hi everyone. We're apparently live, so let's start. Hi everyone, my name is Alex. I'm from Matter Labs, and I'd like to talk about zkSync, or in general about layer 2 scaling with zkRollup, but we'll cover different aspects of it as well. So what happened, as you all know, we have extremely high gas prices right now on Ethereum. I think to send a simple ERC20 token, I need to pay over $3. So like why this happened is also pretty clear. The prices are determined by supply and demand. And right now, Ethereum is in pretty high demand and it's getting very consistent. So blocks are being filled. Everybody wants to use DeFi. Everybody wants to use different other services. Ether itself is rising and we have a problem. The problem is actually known for the last 10 years. So Satoshi mentioned layer 2 scaling for the first time 2010. So why has it been so hard to scale blockchains despite so much time? Like, why don't we have a proper solution on Ethereum till now? It turns out that it's a fundamental problem because the biggest value proposition of layer 1 is resilience. Ask the guys from Libra, ask the guys from Tone. They tried to bring blockchain to millions of users, and they had those users. They could actually deliver, ship the product, and they had very good technology. They could not because of regulatory hurdles, because of like various things where they had to comply. They could not comply. You want to be resilient. Bitcoin and Ethereum work, and nobody stops them because you have lots of nodes. You have like tens of thousands of nodes all over the world in different jurisdictions, which are not subject to any one legislation. And this is what gives them power. So you want to keep this decentralization. It's like extremely important. But that brings a problem that every one of those nodes has to verify every single transaction which is broadcast through a network. They have to go and re-execute everything which is being propagated through Ethereum, which brings us to the definition of scalability. It's not enough to just increase throughput, because if we simply increased ETH block size, we would create a lot of pressure on the full nodes, or like we would raise the requirements to rise around a full node, and we would not be able to have these thousands and thousands of people running them for free. So you want to increase throughput without simultaneously increasing the full node load. And this is scalability. So how do we do this? There are actually only two ways how you can increase scalability without increasing the demands on every node. And they are very simple. Either you let the nodes verify not every transaction, but like some subset of transactions, so you verify less, and then you come up with some sophisticated game theoretical mechanisms how you make sure that it all remains secure. Or you verify the same amount of transactions, but you just spend less resources. For this, you need some technology. So most scaling solutions which were invented over the past 10 years, they belong to the sharding paradigm. So it's obviously sharding at layer 1 level, what Ethereum 2 is going to bring, what the new blockchains like Near are building, but they are pretty far away, and it's really hard to get the sharding at layer 1, keeping all the security at layer 1. Because remember, resilience is top priority for layer 1. So we will still need to see how it works out. But before that, a long time ago, there have been solutions like payment channels, which is an ultimate form of sharding, because every pair of participants maintains their own small shard, sort of. It's like I open a channel with you, we can transact, and nobody else knows about this transaction. So we only settle the final balance on chain. But it's pretty inconvenient because we only can transact two to two. So people came up with ideas like payment channel networks, like Lightning Network, and then sophisticated ways to route the payments through the network. But it created further problems because you need to lock a lot of capital in these networks. So like every time you need to send money to somebody in the payment channel, you first have to put this amount of money on chain for this person, lock it there, and wait for them to receive some transactions. How much money they're going to put there? 1 ETH, 10 ETH, 100 ETH, you don't know. It's complicated, it's difficult to manage, it's pretty dangerous. We had reports from people who were shutting down their Lightning nodes because they couldn't sleep at night, because you have to keep your hotkey, your signing keys online on machines which can be hacked, and it's just a matter of time till they get hacked, and so on and so on. So like, it's complicated. So people came up with very different other ideas, such as side chains, where you delegate the security to a group of validators who vouch with some stake. But some researchers can even not consider it a layer 2 solution because you don't have any security guarantees on your own. It's just a like trusted federation of other people who you give your money in custody. So it's not at all in the spirit of don't trust, verify. There were other ideas. Vitalik Buterin and Joseph Poon proposed a couple of years ago this brilliant thing called Plasma, which promised to solve all the problems because anybody could challenge the validators. So it initiated this idea of fraud proofs for generic networks. But it turned out there are problems with this. Like there were technological problems with Plasma, most specifically the data availability problem, because you only had one operator who could withhold the data. So we'll come to that. We actually made a framework to evaluate different layer 2 scaling solutions. I'm going to put a link to this article under this video, and you can examine it for yourself and just ask the questions and don't take it for granted. Like, go through every question, look at the solution, ask the question, try to dig into like how it's actually working. But most importantly, of all these solutions, and also from all the compression solutions, which use zero knowledge proofs for compressing computations, only 2 stand out because they have data availability on chain. Most of the solutions keep the data off chain without any guarantees, or the guarantees are very vague, or you have to trust to somebody, or maybe you have some complicated mechanisms to exit if your data is not being kept there. But it's really creating a lot of problems. Only 2 things, optimistic rollups and zkRollups, put data on chain, which gives the data the same security guarantees as Ethereum itself. This limits us in the scalability boost which we can gain. So it caps our scalability boost by 100x compared to the mainnet. If that's enough for you, then like if right now a transfer of a C20 token on Ethereum costs $3, in rollups it can cost at least 3 cents. But if that's okay for you, I would highly recommend looking into rollups, because they are better in almost every regard to anything else, which you can then examine yourself. So let's compare optimistic and zkRollups. We actually have a comparison article, which I'm also going to put as a link to this video. But the essential difference is that in optimistic rollups, the operators can publish any state, and if they do something wrong, then anybody, the users, other validators, whoever, can submit a fraud proof and revert the state. But it comes with a number of assumptions. Like you have to assume that somebody is monitoring the transactions all the time. At least one honest person is present and actually checking every single execution. It comes with an assumption that the fraud proof will succeed and that nothing will happen which will prevent this transaction from being mined on the mainnet. And it's pretty inconvenient because you have to wait 1 week till finality on chain. So if you want to make an exit, you will have to wait 1 week. All of this is negligent for zkRollups, because you only need to set up your snarks, trusted setup once. If you're using snarks, if you're using Starks, you don't even need that. It's completely transparent. You don't rely on trust to anybody. If your validity proof fails, you just retry. Like no state transition can happen without a validity proof. And the exits are extremely fast. They only take 15 minutes. What's even like we have a small bonus that zkRollups can use the zero knowledge property of zero knowledge proofs, and we can build privacy easier and much cheaper on top of them. The privacy in optimistic rollups would be at least 1,000 times more expensive compared to zkRollup, because you need to publish all these zero knowledge proofs, and they are large in size. In zkRollup, you can hide them. Both optimistic and zkRollups are being developed actively. zkRollups are live on mainnet. We have zkSync from Meta Labs, Loopring, both operational. So like from every perspective, zkRollup looks better except for one, namely, it's much harder to make Turing-complete programs running, like Turing-complete smart contracts running on zkRollups. So you would need to take your existing Solidity code and change it slightly. With optimistic rollups, it's possible to build optimistic rollups which execute EVM bytecode natively. So it should be easier. It should be doable with minor changes, or maybe without changes in your EVM bytecode at all. But if smart contracts, like if 100% portability is not that important, then, so for example, if you just need payments, then zkRollup is definitely better in every regard, because it uniquely offers passive security guarantees compared to any other scaling solution, meaning that nobody needs to do any work in order to keep your assets secure on layer 2. Like you can just literally go offline for a year, come back, everybody goes offline, then you come back and you have a guarantee that you can withdraw your funds from a zkRollup. So yeah, I'm going to post a link to this article too. You can deep dive into the differences. And let's quickly talk about zkSync, the zkRollup solution from Meta Labs. This is a slide from our Reddit submission. We were one of 18 projects who made a submission, and one of the very few who actually fulfilled 100% of Reddit requirements for like great Reddit scaling bake-off challenge. And more specifically, what is deployed right now on mainnet is a platform for scaling payments. So you can make Ether or ERC20 token transfers in a very convenient way with meta transactions. We have a native multi-sig support. You can send money to any Ethereum address, even if they didn't transact, haven't been registered yet on zkSync. It's going to cost you the same small fee. And you can even interact with smart contracts. So you can send money to an address which belongs to a smart contract, and the smart contract can then control who has access to this money, or you can forcibly withdraw it to layer 1 and so on. The version 2 of zkSync will come with smart contracts, and they will be implementable in Zync, our new programming framework, which is very similar to Solidity and Rust. So it's a language which, if you're coming from either Rust or Solidity background, is going to be super easy to learn, like in one day. This is how the code will look like. Just normally define the function. You do not need to know what zero knowledge proofs are. You do not need to know any math. It's just a very, very simple, very standard programming paradigm. You define your contracts, you define your state, and then you define public and private functions, and you tell them what to do. So if we have a bit more time, then I can show you how zkSync actually looks in action. So let me log out. I can connect with any Web3 enabled wallet, like MetaMask, just by signing a message. And now I have some money on my account. I can deposit more. If I have some tokens, let's deposit some OMG 100. So of course, first I need to unlock the token, and then you can deposit. And while we were waiting for deposit to be mined, I can already make some transaction on layer 2 and send some USDT to some random account. So I can just change the last letter to E, whatever. I make a transfer. I need to sign a message. This is kind of two-factor authentication for a solution. We have a signature from the wallet which you're using, which is being verified on server, and the signature from the wallet which is being verified by zero-knowledge circuits on smart contract. And it's done. Or I could go to a different browser. And this is, by the way, our block explorer from this testnet. But I can go to MetaMask and just copy this address. So this is an account which never transacted on zkSync before, and never transacted on testnet for that matter. And I just send some tokens to this account. It's done. Then I go back and log in to zkSync. And just switch networks. Sign the message. And I got it already here. So I can go and send it back. I need to unlock the account to set the signing key, which is going to be used inside the network. All accounts share the Ethereum address, but have a different signing key for using, which is for using inside zkRollup, because it has to be zero-knowledge friendly. So I send this message, it's instantly confirmed, and I can send half of this amount back. Going back. Did I send it from the wrong account? No, I just received it from here. So the transactions are instantly confirmed, but they're not yet final. They're going to be finalized in 15 minutes or so once the zero-knowledge proof is being generated and submitted to the mainnet. So once I see this double check mark, not a single check mark, it means the transaction is finalized, and now I have all the security properties from zkRollup, which I mentioned before, namely exactly same security like mainnet. Of course, if the protocol is implemented correctly. So we have some cryptographic assumptions. We're using modern cryptography. But if the protocol is, I mean, you always have this with any smart contract, there can be bugs. But if there are no bugs, then nobody can do any game theoretical tricks to take this money from you. Not confiscate, not freeze it, not steal it, nothing. It's yours, like for as long as you want it to be stored there. Yeah, so I think that's it. I will be happy to answer any questions. You can follow us at Twitter, zkSync, or the Matter Labs, and you can go to zkSync.io and just try it out for yourself on mainnet or on testnet. We have open SDK, open API, everything. It's completely permissionless. Oh, you could not see my slides, right? John, are you there?